everybody.
Good afternoon.
Next week we'll be visited by Jason Schenkel. Some of you already know who he is. He is going to depart from his usual plan of delivering the same lecture every semester. And instead of that, will bring us up to date on virtual reality. Today I have the pleasure of introducing you to Dr. Jeremy Gillula from the Electronic Frontier Foundation. And he's going to explain to us how we should and will eventually encrypt the entire web. Let's welcome our speaker.
Thank you very much, Professor Ledeen. As he said, I'm Jeremy Gillula from EFF. I'm honored to be here. So just out of curiosity, as a show of hands, how many people have heard of or know what EFF is? So about half or so. So I'll do a quick just overview of what on earth this Frontier Foundation is. So I'm probably a little bit different from a lot of the speakers at this colloquium in that I'm from a nonprofit. It's not an academic institution, it's not a university, it's a nonprofit that was founded in 1990, and it's not even strictly a computer science organization in the sense that we have a weird combination of lawyers, activists, and technologists all working together, and our basic goal working together is to defend civil liberties in the digital world. So that looks something like trying to defend free speech online. It's kind of obvious now that you have the same free speech rights online as you do in the real world. 20 years ago, that was not necessarily the case. There were court cases saying, can you say the same things online that you can say, in the real world or publish in a newspaper? We deal with intellectual property issues. Copyright reform is a big one. We deal with innovation, so patent reform. But another one here is when security researchers want to analyze some company's device and see, what are the security vulnerabilities. We try to make sure that they don't face legal repercussions for trying to make everybody safer by doing this sort of security research. We work on government transparency, and of course a big one for us is online privacy. So this can range from everything from online tracking by advertising companies to full-scale surveillance of the entire web by the NSA. We are one of the many organizations that are currently suing the NSA over their bulk surveillance and trying to get them to stop basically collecting all of the data that passes through the internet. And that's actually one of the reasons I'm here today is because I'm going to talk about how one of the ways we can essentially put a dent in that is by encrypting everything. So how do we encrypt the entire web? We have an idea for a solution, and the project we call it is Let's Encrypt. So the idea is it's a certificate authority. It'll be free, automated, and open. And the idea is we want to make encryption ubiquitous across the entire web. It began as a merger of EFF working with some folks at the University of Michigan, and then in parallel, Mozilla, the creators of the Firefox browser, had also been working on a similar project. So we sort of merged that together. It's now housed in a separate nonprofit, the ISRG Internet Security Research Group, which EFF is helping to contribute towards. And it's got a lot of major big name sponsors: Mozilla, Akamai, Cisco, IdenTrust, Automatic. I think Shopify, like yesterday, joined as a sponsor. So that's what it is as a project, but what does it actually mean from a technical point of view? So second question to poll the audience. When I say the word CA, how many people know what I'm talking about? Even if you're great. So I'm glad I put this overview in. So I want to start with the question of how on earth does a website actually get this magic little lock symbol? So this is the EFF website. How does it get this lock symbol when you go to it? And obviously this, maybe not obviously, but what this lock symbol means, it means two basic things. One, that when your browser is communicating with whatever server this website is on, the communication is encrypted. Nobody can break into it. Nobody can see what you're saying or what the website is sending to you. But it also means that you are actually authentically connecting to that server. So it's not like someone could jump in the middle and send you encrypted communication and pretend to be that server. That way the communication would still be encrypted, but it would obviously be fake, right? Because it'd be some malicious agent or somebody jumping in and not actually sending data back and forth from the real web server. So how does that actually happen in the real world? So first, the website owner generates a private and public cryptographic key. So these are nothing more than long strings of numbers, and through the magic of cryptography, if they encrypt something with their private key and then put the public key out in the world, then anyone can decrypt it using the public key. Similarly, if they sign something, or sorry, I had that backwards. If they put the public key out in the world and you encrypt it using the public key, only they can decrypt it using their private key. But what's more interesting for this is it can also be used to authenticate them. So if they sign something using their private key, then anyone can use the public key to check that, yes, that's who basically signed that data. It's basically, they create a signature, and when you match the signature, the data, and the public key, it attests to the fact that only the person who had the matching private key could have made that signature. So they generate a private and public key. They create a certificate. So I don't know if any of you have ever looked in your web browser and said, okay, what is, you can go back and you can click on that little icon and look at the certificate. But it's just a text document that contains the public key and some other information. And then they ask a certificate authority. So this is a third party, usually a company or an organization, and they say, hey, can you sign this public key for me so that people will trust me when I send my certificate out to the world? And so the certificate authority, this is a company like VeriSign or IdenTrust or Komodo. You may sometimes see those names up near the lock icon in your browser. They make the website owner prove that they actually control the website that is mentioned in the certificate. So the certificate, in addition to having that public key, says this certificate applies to www.eff.org, and maybe it also applies to ssd.eff.org and some other EFF websites. But it's a specific list, and that way I can't use the EFF certificate and try and spoof that I'm Google, for example. So they make the website owner prove that they own that website, and then they'll go ahead and they'll sign it using one of their keys. And so now we get to, so that's essentially how the certificate gets set up. And so now we get to what actually happens with your web browser. So that's all back end, behind the scenes. You don't actually participate in that when you're browsing the web. But what you do participate in is this protocol called Transport Layer Security, TLS. And so the way it works is your browser becomes pre-bundled with certificates, again, which contain the public keys of a ton of different certificate authorities. So your browser, when you install Firefox, you install Edge, Microsoft's new browser, you install Chrome, anything, you have Safari on your iPhone, it already has the certificates from these certificate authorities. And so what happens is you go to the website, or your browser goes to the website sends back its certificate and says, I was signed by this certificate authority. And you have that certificate authority certificate. You can make sure by comparing the data in their certificate, the certificate authority's public key, and the signature in the certificate. And you can say, oh yeah, okay, the certificate authority definitely signed that certificate. So we know that they at least thought that this was the right website, and they will attest to the fact that those keys belong to that website. So essentially the browser can then, when it wants to send data back to the website, it says, okay, I'm going to encrypt it up with this website's public key, which is in the certificate, and send it back. And no one but the owner of the corresponding private key, which in this case hopefully is the website, will be able to decrypt the data that you're sending back. So if you're logging in, for example, entering a username and password, it'll get encrypted using the website's public key, and then it'll get sent back. For those of you who are super familiar with TLS, you'll know that I'm sort of omitting some steps and compressing some steps. This is a very high-level overview talk, so please please know that I know that I'm compressing some stuff. And in addition, your browser will send back a public key to the website and say, hey, look, when you want to send data back to me, encrypt it using this, and only I will be able to decrypt it. So now both browsers have their keys. And then the website will use the key your browser sent back. And again, as I said, there's a lot more complexity to TLS, but this is the basic idea at a high level, that basically it facilitates an exchange of keys. So, and again, it'll sign, as I said, it will sign the encrypted data using its private key. So it encrypts it using your public key so that only you can decrypt it, but it also signs it so that you know that it was the one who sent the data. So this is great, right? We've figured out how to encrypt data back and forth so that you don't even have to have known that particular website's certificate ahead of time. But magically, you can still encrypt information. Even someone who saw every message pass back and forth would not be able to jump in and decrypt the information, right? This is great. Unfortunately, everything is not so awesome. There are some problems with the state of encryption on the web. One is that TLS, this encryption protocol, is not ubiquitous. Even in today's day and age, even post-Snowden, where we know that organizations like the NSA, GCHQ, and probably plenty of other government organizations, as well as lots of malicious actors, organized crime syndicates, whatever, are listening to the data that we transmit back and forth when we browse the web. And even despite that, TLS isn't ubiquitous. This is if you go to Quora.com, what you can discover is, in fact, when you try to sign in, your username and password are being transmitted in clear text. So not only could some malicious NSA find out what your username and password is, if you're going over Wi-Fi, say you're at a coffee shop and it's open Wi-Fi connection, anyone else on the Wi-Fi could find out your password because they can hear all those packets that your laptop is transmitting. So at least this particular grab was true in June of 2014. So you say, oh, that's a year ago, things have changed, right? No, unfortunately, take a look at this. So this is Google, which you would think would have their, pardon my French, stuff together by now. But if you look, there is no HTTPS up here, there's no encryption, and there's a sign-in link. Now you may say, okay, well maybe if I click the sign-in link, that will take me to the HTTPS website to sign in. But a lot of people won't even bother to check when that happens. And so a malicious agent could interject a link that goes to, basically they could try to spoof Google and interject a link that goes to a non-encrypted sign-in link that looks exactly like Google's, except it won't have the HTTPS. And so they would be able to basically, again, intercept your username and password. And it's the sort of thing that makes technologists like me want to just throw over a table. And this was just a couple months ago. I haven't gone back to check. Maybe they fixed it. I don't know. But the fact that this sort of thing still exists is very, very, very sad. So that's one problem. TLS isn't ubiquitous. So we need to get more, we basically want to get to a point where TLS is ubiquitous, where it's just part of the web. Everything is encrypted so that you can be sure that the information you're transmitting back and forth is authentic and safe from spying. Of course, one of the problems, how many people have tried to set up a web server in here before? So a couple. For those of you who haven't, it turns out that setting up TLS is very tedious. And even for those of you who have, you probably know setting it up is tedious. This is some long set of instructions for how to set up TLS on a web server. We've tried. We've had smart technologists who've been working very intricately with internet-related technologies for 15 years. It takes one of those people several hours to set up a certificate. If you are not an experienced, you may even be a fairly tech-savvy person, but you're just not a full-time sysadmin for a website. It'll probably take you hours or days. If you're a small business owner and you're trying to set up a website and you can't afford an IT staff, good luck. It's infuriating how difficult it is. Worse yet, configuring it is incredibly confusing. When you're setting up TLS, you get to choose all of these different options about the specific cryptographic algorithms that your system ends up using when it talks to the server, or when it talks to browsers, and when browsers talk to it. So you get things like AES-CBC versus RC4. You get all these crazy acronyms that nobody except cryptographic researchers know what they mean, or again, full-time sysadmins. And then even if you know what the algorithms mean, there's frequently new research saying which one you should be using, which one is more secure. You have things like sunsetting SHA-1. I bet, how many people even know what SHA-1 in here is? So one person. And this is the sort of thing you have to figure out when you're running. To most people, they see SHA and they think it's, something entirely different. Then there's things like when new vulnerabilities are announced. Poodle was a major vulnerability that was announced about a year ago now. There's Logjam. There are all these fancy new vulnerabilities that all tell you different things about how to set up your encryption so that it's actually safe. And I have trouble keeping track of it, and I work in this space, so it's incredibly confusing. This is, if you're curious, a long list of the recommended ciphers. So memorize that list for the next time you want to set up TLS on your website. I mean, people write entire books about this stuff. It's ridiculous. Like, it shouldn't be that complicated. Another problem is mixed content blocking. So mixed content blocking refers to the fact that, say a web page is loaded over HTTPS, but of course on any given web page it loads other resources. It has images, it may load up fonts, it may load up JavaScript that it uses, and that's not all embedded in the actual text of the HTML file. It's called externally. It says load this image from a different URL, load this font from a different URL. And if those resources aren't loaded or aren't specified to be loaded over HTTPS, it could introduce security vulnerabilities. So this is an example from Lenovo where it's trying to load fonts, but it's over an HTTP connection, even though the website was over HTTPS. Now, if there aren't any major vulnerabilities in the browser, this may be okay, but what if the website is trying to load JavaScript over HTTPS? JavaScript is basically a fully functional programming language, and someone, again, a malicious agent, could inject JavaScript into the unencrypted connection and could essentially do whatever they wanted to the web page. They could make it look exactly like the authentic web page, have the HTTPS up there, but they could still intercept. They could have a little part of their JavaScript that says, when someone enters a username and password, transmit it to the real website, and also transmit it to my server so that I can steal that username and password. So this is, there's some ideas on how to fix this. One is a proposal for HTTP, a header that a server could send called Content Security Policy. And one of the options for this header is to upgrade insecure requests. So basically it would take a tag like this in the HTML where it says, use this image. Actually, it would automatically, even though the regular HTML says use it over an insecure connection, it would automatically try to do it over the secure connection. This will work sometimes, but sometimes if it's a legacy website, if it's not well designed, it could be that in fact, this image doesn't exist when it's being served over HTTPS because it's actually set up to talk to a fundamentally different server. The web server is configured such that when it gets connections over HTTPS, it treats it like it's an entirely different website. So this doesn't always work, and that's one of the reasons we can't just put HTTPS everywhere we see HTTP when we're looking at HTML. So the last problem is that there are way too many CAs, and they can sign anything. So as I mentioned, the certificate authorities are the ones who we trust to say, yes, that website is who they say it is, and you should trust them. The problem is any CA can sign any certificate. So for example, Google is, in addition to being many other things, its own certificate authority. So when you install Firefox, Chrome, whatever, there is a Google certificate in your browser that actually signs the certificates that Google.com or Gmail.com send when you go look at them. But there's nothing saying that some CA in anywhere in the world, for example, this is, just to emphasize, this is a graph of the CAs and who trusts whom, and this is only a small part of said graph. I think counts are up to now, there are about 1,000 different entities, maybe more, that can sign things that your browser will trust. And these aren't all, well-known US companies. Some of them are, for example, Chinese government-run organizations that can sign a certificate, for example, for Google domains, and your browser will trust it, even though it obviously had nothing to do with Google. Google is not going to the Chinese Network Information Center and saying, sign my certificate, will you? They don't need to do that. And so this is obviously an issue because basically someone could come up with a certificate, convince an untrustworthy CA to sign it, and your browser will trust it. So we have a lot of problems. And this makes me a sad panda. But fortunately, we have, as I mentioned, a solution, which is Let's Encrypt. So the goal of the Let's Encrypt project is to eliminate all the obstacles that stand in the way of getting a certificate and setting it up properly. So we want to make it a lot easier, a lot more trustworthy, a lot simpler to get a certificate, so there are no more excuses. So anyone can just set up a web server and with a few simple commands in the command line on their web server, get a certificate. Or even through clicking a couple buttons on their GUI, get HTTPS on their website. I should mention the target of this project isn't giant companies like Amazon or Google. Even though they sometimes have problems, they can figure out on their own. What we're really trying to do is create a rising tide that will lift all the much smaller boats that are still not using encryption. Now that's not to say they couldn't if they wanted to. I mean, if Google wanted to use Let's Encrypt as their certificate authority, that'd be fine by us. But chances are they're going to continue doing their own thing. It's getting everybody else to get to basically lift the amount of encryption on the web. So Let's Encrypt, in terms of the project, there are three main parts. One is an automated certificate authority server. So as I said, it has to be automated. We don't want you to have to go sign up at a certificate authority and then wait while some human does some interaction with you to verify that you own the website. We want it to be automatic. So we're setting up a server that will automatically issue certificates. And the idea is that you'll have some client program running on your own web server that will go contact this automated CA server and say, hey, I need a certificate. And then they'll talk to each other, and they'll talk to each other over what we call the ACME protocol. It's the Automated Certificate Management Environment Protocol. And it's basically just, the idea is it's an open protocol that these two pieces of software can use to talk to each other, so that this one can say, hey, I need a certificate, and this one can say, okay, hey, prove to me you own that domain you're requesting the certificate for. This one can say, okay, here's my proof. This one can say, okay, I accept your proof. Here's your certificate is signed. And then this one will say, okay, thanks for the certificate, and it will automatically set it up on the web server. So that was the 20-second super compressed version. Let's go into how this actually works. So again, as I said, the first problem about TLS not being ubiquitous, the idea is to make it super easy. So it's automated. Oftentimes, especially if you're a business, you have to buy a certificate. You have to pay several $100s. Sometimes it's as cheap as, if you're using it for personal use, you can get a free certificate often. But if you're a business, it costs money. And if you're a small business, you may not have the money for that certificate. You may not think it's worth it. So we have this automated certificate issuance server. It's free. And it speaks this open protocol. So other certificate authorities could adopt this if they wanted. IdenTrust, VeriSign, these other companies could decide, hey, look, we will adopt this protocol, so we don't have to be the only ones talking it. But regardless, so that's the idea. Now, how does a CA, including us, know that somebody actually controls the website, the domain that they are trying to get a certificate for? So if EFF.org wanted to get a certificate and we went to somebody, how would we prove to them we control it? Well, currently the typical answer, at least for the minimum security, is something called domain validation. So what the certificate authority will do is they'll send an email to some canonical email address at that domain. So admin@EFF.org or webmaster@EFF.org. And that email will contain essentially some long magic string, and and it'll have instructions saying post this string at this specific location on your website, and once it's there, that's essentially proof to us you control the website, because if you didn't control the website, you wouldn't be able to post it there, and only people who actually control the actual physical machine that is serving this domain would be able to manipulate it in such a way that they can get the file posted. So essentially they say post this nonce at this address, tell us when it's up, we'll go check, and if we see that it's there, then that means that whoever we emailed obviously has at least enough control of this website to post stuff, and that's essentially the assurance we have that you control this website. In Acme parlance, in the protocol we've developed, this is called a challenge. So we're essentially challenging the owner of the website to prove that they control it. This is not very reassuring. This is for a couple of reasons. One, this is kind of like throwing a message down a long dark hallway. You don't know what's off at the other end, saying, flash me, with your flashlight this Morse code signal, and we'll assume that it went to the right person who controls everything at the end of this hallway. The other issue is what happens if someone, again, like an NSA, GCHQ, is trying to get a Google certificate. And remember, this process has to be automated, so there's no humans who can use common sense in the loop here. So say NSA was trying to get a Google certificate so they could, target some terrorist and look at their Google account information. They could basically sit on the wire that is just coming out of our building. They could sit on our internet connection and intercept all of the emails we send out or the challenges we send out, and basically also intercept all requests that we make to the specific website. So someone could, say they wanted to get Google, they would sit on that wire, transmit a request saying, we want to get this google.com certificate signed. We would say, okay, post this specific string on your website. They would say, sure, we did it. And then when we went to make the request, they would intercept the request we would have to see, okay, what is at that location on the Google website. And they would spit back at us, essentially, this fake answer. No one else on the web would see this because they're just trying to target us. So our answer to that is to use multipath domain validation, which is slightly better. Now it's 3 different, or however many different kind of scary hallways, in that we can use different points around the internet to see, did the website actually post that thing? Do we get the same answer back no matter where we are on the internet when we request that file from the website to prove that they received that challenge? And so this is one way to get slightly better assurances, so that in order to get by this, someone like the NSA would have to intercept a ton of different requests, and at that point they could just spoof Google generally anyway. Once they're on, once they're basically spoofing it across the entire internet. Alternatively, if they were spoofing it across the entire internet, people would notice too. So it's much harder to do a targeted secret attack. But we can do even better, since domain validation is still scary. And we can do better because some websites will already have a certificate. Or if they want to get a new certificate and they've used Let's Encrypt before, we will have already given them a certificate. So that means domain validation's already happened. So now what we can do is someone has already proved ownership of that domain. So we can chain off of that. And so we can say, hey, look, you already have a certificate, which means you already proved that you control the domain. So why don't you just show us that you, instead of proving to us that, with this sort of scary, non-encrypted domain validation setup, why don't you just prove you have the private key associated with that certificate? So this is a different type of Acme challenge. This way, now instead of relying on us not getting spoofed, we're relying on the fact that this website kept its private key secret. And so we say, hey, why don't you sign this with your private key and post it? And then only you could have signed it with your private key, and then we'll look at the corresponding public key. And this way, domain validation only happens once. After that, it's pure math that proves, essentially it's pure cryptography that proves that you do own this website. So the question, of course, is how do we know whether or not a website has an existing certificate, especially if they haven't used Let's Encrypt before? The NSA could still spoof Google with try to spoof it with a certificate, or maybe they got, maybe China is spoofing using their ability to sign certificates to spoof a certificate. And again, they'd sit on the wire, they'd intercept our requests, we'd be out of luck. The answer is we have something called the SSL Observatory. So what this is actually a database of essentially all of the certificates that have ever been seen anywhere on the web. It's made up of a bunch of different sources. So if you've ever used EFF's HTTPS Everywhere browser extension, chances are you have anonymously sent us the certificates that your web browser has seen. So it will send back to us the certificates anonymously. And then we build up a collection. And so this way we can see, hey look, some people are seeing a fake Google certificate. So that can't be authentic. But we also see, hey look, Google, in 99.99% of the cases has issued this certificate when people try to go to it. At the same time, we can scan the entire internet. We can just connect to every IP address on the internet and say, hey, do you have a certificate? If so, give it to me. And we can collect certificates that way. There's also another project, Certificate Transparency, CT, which is yet another project, this one is spearheaded by Google, to introduce transparency to the whole certificate ecosystem. So long story short, we essentially have a huge database of existing certificates. And this, I guess, that's TOFU, trust on first use. So basically, the first time someone tries to prove that they own a website, we trust them, essentially. And then after that, we don't have to trust them anymore because we can prove whether or not they control the website. So that was all just to get TLS issued, just to get certificates issued. How do we make it easier? One way is to provide this client I talked about that basically gets HTTPS configuration right. It's a simple command line interface, and so the idea is you're on your web server, you install our client software, and it will automatically tweak your server. Maybe you're running Apache, maybe you're running Nginx. These are basically popular web server packages. And it will tweak the server to pass the challenges. It will automatically contact our software, say, hey, we want to install this cert, and it'll do it automatically for you. So you don't even have to think about it. It'll install the resulting certificate for you. So you don't have to know, where on the file system do I put it, what do I name it, does it have to be named something special? It'll take care of that. It will tweak the security options, so you don't have to know what the difference between SHA-1 and SHA-256 or RC4 or any of this stuff. It will automatically say, based on the current knowledge we have, these are the best options. And then, last but not least, it'll also automate some of the security tasks. So what sort of tasks will it automate? So again, as I mentioned, cipher tuning. So choosing what type of cryptographic algorithms you use. It can automatically set up this upgrade insecure flag I talked about a little bit before, as well as something called the Online Certificate Status Protocol stapling. This is just a fancy way of saying that periodically your server can contact the CA and say, hey, can you sign this statement saying that this certificate is still valid and hasn't been compromised? And then that way, if you can be sure that, because a lot of times certificates will be valid for years, and when you're on your web browser, you want to know, is that certificate actually still valid, or did it get compromised? Did someone steal the private keys? Did someone sign it improperly? So we can take care of that for you. It'll do it automatically. Slightly harder, we can do redirect. So we can automatically redirect people who try to go to your website over HTTP. We can redirect them to HTTPS. We can also automatically renew your certificate. So this way, instead of having a certificate that is valid for years, you can say, I'll just have it valid for a week, and then I'll get a new certificate in a week. And it'll happen automatically. It's free, it's automated, it doesn't matter, it doesn't take me any extra work. And this way, if your certificate is compromised, the window of time in which it's valid, even though it's compromised, is very small. And so it's much less value to compromise the certificate. A little bit harder is doing full rewriting of the content, doing HTTP strict transport security, which is, again, it's another protocol for telling browsers, only connect to my server over HTTPS. And even harder is actively trying to find areas where there's mixed content. Because the mixed content might not just be in the text of the HTML file, it could be dynamically generated in the JavaScript that your website runs. And of course the last problem was that CAs are terrifying. So there are a couple different ways that we try to get around this. I should mention running our own CA is just as terrifying as the fact that there are so many CAs out there and that they can sign whatever they want. We try to defend ourselves increase our security as much as possible. But there's a saying that there are two types of companies out there. The ones that know they've been hacked and the ones that have been hacked but just don't know it yet. And so you have to assume that at some point you're going to get compromised. And the question is, how quickly can you recover from that compromise? And how can you minimize the damage when that happens? So the major way we're tackling this is through transparent operation. So for example, we're going to be publishing the Acme server logs. So if someone compromises us and say issues a certificate via our server, then people out there can look at the logs and say, hey, wait, that certificate probably shouldn't have been issued because my website never actually asked you for that certificate. Similarly, we would be able to see if someone else out there was trying to pretend to be us when issuing certificates. In a similar vein, we'll be publishing a verifiable history of all the certificates we've issued so that, again, people can, other security organizations can audit us and say, these are the certificates we've issued and these are the only ones that people should see. We're going to, again, publish to the certificate transparency logs, which is another way, it's actually a distributed way of publishing what certificates we've issued, what certificates web browsers have seen, and what certificates web servers are serving up. So these are all ways, essentially, to ensure that what we say we're doing is actually what we're doing. In terms of protecting from other CAs, as I said, a CA can sign for any website. One way to get around this is something called HPKP, which stands for HTTP Public Key Pinning. The idea is that when a browser first goes to your website, it not only gets your certificate, but it gets a little message that says, and in the future when you connect to me, only accept this certificate. And if you see a different one, you're being attacked. The reason this is a little scary is because if you ever have to change your certificate, you have to go through a very complicated dance to make sure that it's still valid, and you have to tell browsers, I know I told you only to trust that one certificate, but actually I've signed this new certificate with that old certificate, so now you should trust this new one. And so it's complicated, it's a little crazy, but if you want, we will support it. And last but not least, in general, one of our big ideas about protection is to support rapid rekeying and recertification. So for example, say something like, how many of you at least heard of Heartbleed when it happened about a year ago? So basically this was, all of a sudden, it turns out that this one piece of software is insecure, that all these servers are using, and so all of their certificates might have been compromised as a result. And this has nothing to do with us as CAs. This wasn't our fault. This was the software the server was using. But what we can do in that case is, instead of everyone manually have to going in, and request a new certificate, we can push a notification out that says, hey, we think your server might have been compromised. Why don't you automatically request a new certificate once you've updated your software? And maybe the client will even automatically update the software for you. Once it detects that the new version has been installed, it'll say, okay, now I need a new key. Now I need a new certificate. So you don't even have to think about it. You don't have to be a security professional. Similarly, if we get compromised and we discover it, we can create a new certificate, a new key, and push it out and say, look, I'm sorry we got compromised, but let's just re-sign everything. It's all automated, so it doesn't matter. It matters that everything that is already out there is compromised, but we will, from this point forward, be safe because we're automatically pushing out new certificates. So that's the idea: security, usability, and transparency. Now you may say, sign me up, I'm ready. I have a website, I have a server, I want to sign up. We're not quite ready yet. We issued our first certificate just a week and a half ago, actually. This has been ongoing for a couple of years now, and we're almost there. If you want to check it out, you can go to helloworld.let'sencrypt.org. Note that it will not yet be valid in your browser. We're working, that is the next goal, which will happen about mid-October. So you have to go through a few extra steps if you want it to be valid in your browser at the moment. By mid-October, our certificates that we issue will be valid. And if you want to be part of the beta program, you can go to eff.org/let'sencrypt-beta and sign up. And you can be one of the first websites out there that has a free automated certificate. And by mid-November of this year, we're shooting for general availability. Alternatively, if you actually want to help out and you're familiar with the language Go, because it's all written in Go for reasons that escape me, you can help out with the spec. Again, that's the Acme protocol, or you can actually hack on the client and server. And so in addition to the protocol being open, all the software we're running is open source. I don't even know what license it is. It's probably, Apache, maybe it's GPL, I don't know. Anyway, long story short, you can download the code, you can look at it, you can add to it, you can basically help out with this. So that about concludes my talk. I am happy to take questions both about Let's Encrypt or just general other EFF issues or what it's like to be a technologist working with a bunch of lawyers. The quick answer is very interesting. So yeah, thanks very much for having me.
We have time for a couple of questions.
No question is too dumb. If something totally went over your head, ask it, because I guarantee you there are at least 5 other people in the room who have the same question.
So you said your funding comes from the companies that you mentioned in the beginning, or?
For the purposes of Let's Encrypt, EFF has different funding. So that's the funding for this nonprofit spinoff, ISRG, which is housing it. Because we don't, as EFF, because we do a lot of other things, we don't want to be a full-time CA. So we got the project started, but then are passing it off to a actual, in the same way there's the Linux Foundation or things like that. And they are funding that thing. EFF's funding comes primarily from individual donors. Only, I think, about 5 or 10% of our funding comes from companies. It's almost entirely from individual members. Mm-hmm.
Does domain ownership imply that I have the web server in my office and I'm running it, or am I leasing it from a domain host?
You could be leasing it. It basically means, so essentially what we're trying to get at is that you have root access on that server. Is fundamentally what we're trying to get at. Because if you have root access, you can make the server respond to queries, to incoming requests with anything you want. And so that's essentially what we're trying to get at. We're assuming that only someone with root access will be able to configure a web server. So you have to run the client as root to make it do its things. So you can totally host it on Amazon or anything like that. But instead of using their HTTPS option, which may cost money, maybe you don't trust them for some reason, you could totally use Let's Encrypt. Mm-hmm.
Some of this kind of feels like security through obscurity. So are you guys trying to make a procedure or protocol so that it is secure and have some kind of methodology for it?
So that is the idea with the Acme protocol. Is that it's been we've actually had a couple different external security audits about it, and I would actually push back on the security through obscurity, at least for the Let's Encrypt project, because we are putting absolutely everything out there. We're putting our server software out there, which is that is the code that is automatically giving certificates out to people. We're putting the protocol out there. We're putting the client software out there. So absolutely everything is open. I don't know what else we could do to make it more open.
So if I have a server, but it doesn't have a domain name, but it uses some website that takes the dynamic IP address and attaches it to like its own domain name type thing, will it still work for that?
I think it'll work with, so it depends. So one of the things we are checking, so first of all, I'm pretty sure we're not going to issue anything to IP addresses. So you wouldn't be able to say, I control, this specific IP address. We won't sign certificates for that. We also probably will not sign, I have to go back and double check. So there are things called, what's the word? Public suffixes, which is things like .com or things like .dynamicdns.org or something like that, or something.amazon.com, because that's where you get this dynamically generated DNS name for your server when you host on Amazon's cloud. And I'm pretty sure we're not going to be issuing for those because of the fact that it's very easy to lose control of such a domain, and then someone else can get it and try to spoof you. So I'm pretty sure we're not going to for that, unfortunately. But I'm not 100% sure on that. So I'd have to go back and check.
Other than latency, do you have any criticisms of onion routing?
I mean, so that is a huge question. In terms of, not personally. I mean, so far I think it's probably the most analyzed in terms of security and the most responsive in terms of getting upgrades and patches, in terms of systems out there for using the web anonymously. So that's actually the one I would recommend if you're trying to use the web anonymously. I'd recommend you do it through the Tor browser bundle. I definitely have criticisms with trying to just pipe all traffic through Tor and hoping that you don't get unmasked.
Well, thank you again.